Hi everyone, my name is Dancheng and I'm a PhD student from King's College London. I would like to use this opportunity to thank Dr. Andrew Coles and Dr. Amanda Coles for supervising this project. And today I'll be presenting our project on learning macro actions to improve the relaxed planning graph heuristic. Macro action is a meta action built from a series of actions. For example, if you have an action pick and another action drop in the same domain, then the action pick and drop can be an example of a macro action. The heuristic computation process can be improved by using macro actions because of the plateau escaping effect. A plateau is encountered during heuristic computation when the planner cannot find any successor states with strictly better heuristic values. When a plateau is encountered during heuristic computation, the planner usually has to do exhaustive search in order to find an exit to the plateau, and this is going to be a very expensive process. By using macro actions, the planner would be able to jump ahead and find an exit to the plateau in a shorter period of time. However, including macro actions will increase the bunching factor of the search process. This means that the planner has more possibilities to consider during the search process, and it will have a negative effect on the planner's performance. Therefore, in our project, we explore the effect of macro actions on the planning process when they are included in the domain but are excluded from search. We use the fast downward planner and we slightly modified it so that it's able to identify macro actions and is able to exclude them from the search process. In our paper, we have presented two learning methods. The first one is more of a systematic approach, while the second one is a local search approach inspired by parent iOS. Our paper has experimental results to show that it is possible to learn macro actions that can improve the planner's performance in a range of benchmark domains, even when macro actions are excluded from search. The first step of our project is to generate macro actions, because they are not naturally included in the domains. We have developed a program that can automatically generate macro actions for arbitrary domains. Unlike previous macro action generators, we aim to generate macro actions without using problem files and solution plans because we are not looking at macro actions that can be used during search, but looking at macro actions that can be used in heuristic. The first learning method is a systematic learning method. The aim is to explore whether it is possible to use macro actions to improve the planner's performance at all when they are not used in search. This is a multi-round approach. So the first round compares all macro actions comprising two primitive actions, and in subsequent rounds we will explore using longer macro actions and expand the number of actions in the domain. This is a summary graph of the systematic learning process. In the first round, we will use only two primitive actions from the original domain to generate macro actions and compare all of them to find the best one. And in subsequent rounds, we will use the best found macro action from the previous rounds to generate longer macro actions and compare all of them to find the best one. After the learning process, the learned macro actions were evaluated using both the benchmark problems as well as larger problems. The larger problems were randomly generated using the problem generators of these benchmark domains, and they all take more than 70 seconds to solve using the original domains. They were generated because we found that the benchmark problems sometimes were not large enough to evaluate the learned macro actions fairly. The evaluation results are presented in tables. The IPC scores are calculated for both the original domain as well as the domains with the learned macro actions. The first table shows the IPC scores of the benchmark problems, and the second table shows the IPC scores of all of the evaluating problems including the benchmark problems and the more complex problems. As you can see from the tables, the better results are almost always seen in domains with macro actions, which means that our systematic approach is actually an effective approach to learn useful macro actions. And during the experiments, we realized that macro actions not only helps to improve the heuristic, it also helps to improve the SAS plus formalism. The fast normal planner has this feature of translating PCL domain into SAS plus formalism before the actual planning process. And by including macro actions, the SAS plus outputs change sometimes. Therefore, we have this translator-only configuration for the experiment. In this configuration, we will remove the macro action from the SAS plus formalism. This means that the macro actions are only used for the translation process. And as you can see, the satellite domain and the single travel domain actually have their best performance found in the translated-only configuration. This means that the macro actions learned for these two domains are actually more useful in changing the SAS plus formalism rather than being useful in the heuristic. The next learning method is a local search method based on parent iOS. The systematic learning approach takes too much time and only uses 3 problems for each domain. It might lead to overfitting issues. Parent iOS is a framework that aims at identifying the optimal configuration of a given algorithm. Parent iOS relies on randomness to find the optimal configuration and is adjusted to work with AI planning and macro actions. Here I will just present some of the most important changes that we have made to the original Parent iOS framework. The original domain is used to generate an initial set of macro actions which only consist of 2 primitive actions. The neighborhood of a domain consists of the following 2 types of domains. The first type is to remove one macro action from the current domain and add one other macro action from the initial set of macro actions. The second type is to keep all macro actions in the current domain and add one other macro action from the initial set of macro actions to the current domain. Additionally, we set the limit m to be the maximum number of macro actions allowed in a domain. The objective value of a domain is calculated by either the mean or median planning time across n training problems. In our experiments, we found that the useful macro actions learned from the systematic approach don't always perform well on all of the training problems that we use for the local search learning approach, even though those macro actions are proved to be useful during the evaluation phase. If our objective values are only calculated by the mean planning time, the performance of these useful macro actions can be badly affected by the training problems that they cannot solve. Therefore, in our experiments, we consider both mean and median planning time for calculating objective values. The iterative first improvement process is also modified. The original process will look at every member in the neighborhood for a configuration, but in our experiment, we found that the neighborhood sizes are too large for the augmented domains. So the process is modified to only consider a randomly selected n number of neighbors rather than iterating through the entire neighborhood. The dominates function is also modified. The original dominates function says that one configuration dominates another one when the objective value of the first one is better than the second one. But for our experiment, we found that a lot of generated domains actually have very similar performance, and we don't really want a domain to replace another one just because there is a slight improvement. Therefore, for domain 1 to dominate domain 2, the objective values of them have to be significantly different. When the objective value is calculated by the mean planning time, Domain 1 and 2 are significantly different if the difference between the sum of their planning time across n problems is at least the value defined by this formula here. The d value is actually different for different configuration of our experiments. And when the objective value is calculated by median, then domain 1 and domain 2 are significantly different if the difference between their objective value is at least 1. The details of the different configurations that we have considered for the experiments as well as their evaluation results can be found in our paper. Here I will just present a summary of the best seen IPC scores when the objective values are calculated by mean and when the objective values are calculated by median. As you can see from the table, no matter whether we are calculating objective values by mean or by median, we will always be able to find some domains with better IPC scores than the original domain. Therefore, this shows that the local search learning approach is also an effective approach to learn macro actions that can help to improve the planner's performance. So in conclusion, we have shown that it is possible to learn macro actions that can improve the planner's performance even when excluded from search. We have presented two ways of learning such macros, and were able to show improved performance in a range of benchmark domains. For future work, we will continue to look at how best to configure the local search learning process. We will look at different heuristics and other different benchmark domains. We can also compare the results with macro actions generated by other generators such as MacroFF and Marvin. Thank you.